Okay, this is my house. You might have noticed that, and not my office. So let's get this thing done. Colligative properties. What does this mean? This means the difference between a pure solvent. So I have something pure and now I have a mixture, I have a solution. What's the difference between a pure solvent? Because if you look on the periodic table, it will give you boiling point and freezing point, and it will give you all kinds of information about a pure solvent. What happens when you add two pure solvents together and make a solution? You get colligative properties. You get different properties. This is what happens when you add two pure substances together. You get a colligative property. This is a property of a solution that depends only on the number of dissolved particles. So at this point, we no longer care what it is. We no longer care what the two pure solvents are broadly. We don't care. What we're saying is when we put the two things together, now we're just looking at number of particles. It doesn't matter what those particles are. We're saying now there's a whole mix of particles and we're counting concentration more than we're counting pure solvents. So what does this do? Vapor pressure is lower. Why? What does that mean? It means this. I have this handy little thing for you to see because I think it's funny. Can you see that? I don't know if that is on your screen, but it's really funny. Calm down and stop trying to evaporate because non-volatile solutes, they lower your vapor pressure. Stop trying to evaporate. So what is happening, now I don't know how to get this off your screen. So what happens is everybody's trying to evaporate, right? Vapor pressure is trying to evaporate. So everyone's trying to evaporate, but what's happening? Remember, how do you evaporate? Oh, I don't have a glass of water. If I did, I would show you. You have a glass of water. Let's say I have a glass of water in my hand, and the little particles are, remember they're hitting me in the face. The little particles are trying to evaporate. They're bouncing off out of my cup. Well, now there's all kinds of other particles in there. It's not just one. It's like all of a sudden there's a bunch of stuff going on in there. And the bigger particles at the top are preventing the little particles from bumping up. So this is true. For example, the more particles that are happening in there, the lower the vapor pressure. So you leave ethanol or acetone, fingernail polish, you leave it open, it's gone, right? Then you leave water on your desk, and like the next morning there's less. But like Coke or something else that has a higher amount of particles, it doesn't evaporate as quickly. So that's an example of how that's working. Okay, boiling point is higher. So what do I mean when I say boiling point is higher? I mean it takes more energy for it to boil. You have to boil it longer. You have to boil it at a higher temperature. It takes longer to boil when you have a bunch of stuff in there. It just does. Try it out. Put some salt in there, put some sugar in there, put some oil in there, put some stuff in your water, and you will get, it will take longer to boil because there's more things going on. It's the same reason that your vapor pressure is that way. So you have it's boiling, it's trying to get out, and you have all these things dragging it down. Think of that. Think of like there's bigger particles at the top, and these little guys are trying to get out. I'm trying to get out, but the big ones, they're bouncing onto the bigger ones or the different ones. There's just more things for them to bounce into and bounce back into solution before they can be free to boil and evaporate. Freezing point is lower. Okay, why would freezing point be lower? Let's think about it. Freezing point is lower. So this means it takes more energy to freeze your ice pops. So if you get two ice cube trays and you fill one full of water and you fill one full of grape juice or something, it will take longer for the grape juice to freeze. It just will. There's more things trying to balance out, because remember they have to become kind of a crystalline, so they all have to line up in a like nice orderly fashion. And it takes longer when there's a bunch of different sizes and everybody's pushing on each other, and it takes a lot more energy and it takes a lot longer for that to happen. So that's sort of the why. There's more things going on, there's more things it's bumping into. And that's the same for vapor pressure. So I Do I have anything on that? Again, it depends. Wow, I'm not even trying. Depends on the equilibrium between molecules entering and leaving the solution. We will fix the way things are spelled, and I will put it in red, and I will even make it bold for you. Look at that. Okay. That is vapor pressure, and it's the same thing. Boiling point is going to be similar. I'm actually going to put, no, heated, if solvent, let's do this. If solvent molecules are replaced by solute, the rate will. If solvent molecules are replaced by solution, the rate will increase. And the freezing point is the same thing that is on the next page. But it's just the same concept. It's just what I just told you. Again, additional molecules make it harder to rearrange into a solid structure. So this takes longer. Okay, osmosis and osmotic pressure. So this is super fun. But remember, just remember, take a second and remember lab. I don't make you do lab for no reason. There's a reason. Actually, I put some thought into it. So the lab asks you a couple times the difference between osmosis and dialysis. Osmosis is just water. So we didn't do osmosis in class. We did dialysis. Osmosis is the idea that water is going to rush in. Water is going to try and dilute something. Water is going to go where the concentration is higher. And water is going to be like, let me dilute you. My job is to dilute you. So it's going to go from a hyper concentration. So what does hyper mean? If you think of people who are hyper, like they've had too much caffeine. They've had too much of something. Too much of something is happening, and that's why people are hyper. So hyper is the thing that has too much. So the hypertonic solution has a bunch of something. And the water is trying to rush in and like, goodness, dilute the caffeine. Just so you know, I did some tie-dye. That's why my fingers are crazy color. So a hypertonic solution, so let's say in here it's a hypertonic solution, water is going to rush in there to try and dilute the hyper. So hypo, hyper. That's what's going to happen. So osmosis and osmotic pressure, this is super important. We're going to talk about this in physiology a lot. It's related to your interstitial fluid. It's related to like everything that happens between your cell and your blood. This is a big thing. So you need to sort of try and understand it. If you don't, ask me, get online. I have videos. I have other things you can do, but you really need to understand this. So osmosis occurs when a solution is separated. Why can I not get the rich to stay? Separated from a pure solvent by, oh, come on, take a guess. You know this. You know. Come on, semi-permeable membrane. Did I really spell that wrong? Are you kidding me? Did I spell permeable wrong? Why is it doing that? There we go. Semi-permeable membrane. Okay, semi-permeable membrane. So anything, so I have my cell or my thing that's hypertonic because there's a bunch of stuff in there, and it's separated by a membrane. What's my membrane gonna let in? Just water. It's not dialysis, it's osmosis. Just gonna let in water, and then it may expand or contract, but it's just gonna let in water and gases. Just water. That's it. That's all it's letting in. Okay. So this little thing is telling you what's happening. So inside my semi-permeable membrane, I have some kind of concentrated solution. I have syrup or something in here. Doesn't matter. I have something awesome. I have Dutch Brothers caramel latte in here. And it's separated by a semi-permeable membrane. Because in here it's hyper, right? It's hyper, there's coffee in there. So where's the water going to go? The water's going to go in there. So this thing is just telling you where the water's going. So over time, the water's going to rush in here, and the water's going to push up this little straw. Yeah, that's what's happening. So here's the water. It's rushing in because this is the hypotonic solution. This is the hypertonic solution. We will talk about this with your blood cells in just a moment. Osmotic pressure. Osmotic pressure is the amount of external, wow, it's late at night, external pressure that must be applied to a solution to prevent net movement across a semi-permeable membrane. And I spelled movement wrong. Seriously. Okay. So this we're actually measuring the pressure of this. How much pressure? So when we talk about your blood moving, we're going to talk about osmotic pressure. We're going to talk about hydrostatic pressure and osmotic pressure and the beauty of these two things that come together that actually clean your blood. It's really fun. So that's a little something to look forward to. You should stay with me and take physiology. So osmotic pressure, the amount of external pressure that must be applied to a solution to actually prevent the net movement across. So how much pressure do you have to apply to get it to stop doing that? It's a weird definition, but that is the actual definition. And I have this is the equation related to it. I don't think I gave you any problems like that in the homework, but I might have. I did not, however, give you those problems on the test related to this equation that I remember. But osmotic pressure depends only on the concentration of the solute particles. So there can be a concentration in the solvent, but it's really just related to the solute, the difference between the solute and the solvent. When a solvent and a solution contain particles and they're separated by a semi-permeable membrane, the solution is said to have a higher osmotic pressure than the pure solvent. So that's where you get osmotic pressure. Let's talk about osmolarity. So osmolarity, actually I don't want to talk about osmolarity until the next video, which shouldn't be very long, but I don't think I can do it in 2 minutes. So I'm going to stop this one, and I know you're just like on pins and needles. I want to know the definition of osmolarity. Tune in, it's coming.